해주시면 대단히 감사드리겠습니다. 예. 개최식 및 특별 강연을 시작을 하도록 하겠습니다. 안녕하십니까. 저는 2023년 대한건축학회 추계학술발표대회 개최식 및 특별 강연의 사회를 맡은 건축학회 총무담당이사 한양대학교의 이강석입니다. 인사드립니다. 오늘 바쁘신 중에도 불구하고 23년 건축학회 추계학술발표대회에 참석해 주신 회원 여러분과 내 외빈께 깊은 감사의 말씀을 드립니다. 학술발표대회는 아시는 것처럼 건축 문화 및 건축 산업 미래 비전을 제시하고 건축인 모두의 교류와 화합을 도모하기 위하여 마련한 자리입니다. 이러한 자리에 건축계의 많은 선배님, 후배님들 포함 동료분들과 함께 할 수 있어서 대단히 영광스럽게 생각합니다. 그럼 지금부터 2023년 대한건축학회 추계학술발표대회 개최식을 시작하도록 하겠습니다. 먼저 국민의례가 있겠습니다. 모두 자리에서 잠시 일어나 단상에 있는 국기를 향해 주시기 바랍니다. 국기에 대한 경례.
나는 자랑스러운 태극기 앞에 자유롭고 정의로운 대한민국의 무궁한 영광을 위하여 충성을 다할 것을 굳게 다짐합니다.
바로 모두 자리에 앉아 주시기 바랍니다. 다음은 바쁘신 중에도 불구하고 학술 발표대회 축하를 해 주시기 위해 가지고 참석하신 내빈소개가 있겠습니다. 소개를 드릴 때마다 큰 박수로 환영해 주시면 대단히 감사드리겠습니다. 먼저 대한건축학회 김광우 전 회장님 참석하셨습니다. 큰 박수 부탁드리겠습니다. 그리고 오늘 소중한 특별 강연을 해주실 나카노 요시아키 동경대학교 교수님 참석하셨습니다. 박수 부탁드리겠습니다. 그리고 오늘 대회장이신 건축학회 최창식 회장님 참석하셨습니다. 큰 박수 부탁드리겠습니다. 이 위에도 많은 분들이 참석을 하셨지만 시간 관계상 일일이 소개를 드리지 못하는 점 대단히 송구하게 생각합니다. 양해 부탁드립니다. 다음으로 23년 추계학술발표대회 대회장이신 대한건축학회 제40대 최창식 회장님의 개회사가 있겠습니다. 단상으로 올라오실 때 다시 한번 큰 박수 부탁드리겠습니다.
예, 여러분 안녕하십니까? 본격적으로 그 인사 말씀을 올리기 전에 제가 서울에서 이렇게 그 하이원으로 넘어오는 과정에 좀 이번은 특별히 가슴이 좀 설레곤 하였습니다. 그 이유는 강원도 정선이라고 하는 곳, 또 카지노가 있는 하이원 리조트, 어쩌면 상당히 로컬 에어리어인데 대한건축학회 추계학술대회를 여기서 진행하는 것이 여러 가지로 어려움이 따를 것이다 이렇게 생각을 했었습니다. 근데 오는 과정에 마음이 굉장히 설레기도 하고요. 마침 이 하이원 리조트에 들어서면서 바라다보는 이 전경은 최근에 저희들이 바쁜 일정 속에서 느끼지 못하는 아주 풍요로운 그런 마음을 주었던 것 같습니다. 예, 준비된 이 개회사를 시작하도록 하겠습니다. 조금 전에 말씀 올린 바와 같이 오색 빛깔 곱게 물든 단풍잎과 푸르른 하늘을 보니 더욱 풍성하고 아름답게 느껴지는 계절 가을입니다. 우리 건축학회의 2023년도 추계학술 대회를 이곳 멀리 자연환경과 청정함으로 유명한 강원도 정선에서 진행하게 된 것을 대단히 의미 있게 생각을 합니다. 더욱이 강원도는 올해 6월 강원 특별자치도로 개편되어 우리 학회 추계학술대회와의 의미로 본다면 같은 의미로 남다르지 않다고 생각을 합니다. 먼저 이번 대회에 성공적인 개최를 기원해 주신 김강우 전임 회장님, 이곳 멀리까지 왕림해 주셔서 특별히 감사드리겠습니다. 조금 있다가 아마 바쁜 일정이라 참석은 못하시지만 축하 영상을 보내주시는 김진태 강원도지사님, 그리고 특별히 존경하는 김은영 강원대학교 총장님께도 미리 감사의 말씀을 전해드리는 것이 순서일 것 같습니다. 유관단체에서도 오늘 많이 오실 텐데 아마 지금 오고 계실 텐데요. 아마 한국건축가협회의 아마 천희영 회장, 그 다음에 한국건축구조기술사회 고창호 회장, 그리고 교육시설안전원의 박구병 이사장 아마 참석을 해서 우리 학회를 더욱 빛내주실 걸로 생각을 합니다. 감사한 말씀을 전합니다. 우리 학회의 학술발표대회는 건축 문화와 다양한 학문 분야에서 그간 준비해 오시고 연구해 온 결과들을, 그리고 또 건축 문화 창달과 건축 기술의 발전 방향을 제시하는 것을 포함해서 역시 뭐라 해도 학회다움은 학술대회를 개최할 때 그 의미가 두드러지는 듯합니다. 이번 추계학술발표대회에서는 우리 회원들께서 그간 연구해온 많은 논문들, 그 중에서도 논문 460편이 구두 및 포스터로 발표할 예정이고 발표가 진행될 것입니다. 무엇보다 저는 의미를 두는 것은 우리의 미래의 자산인, 우리 미래의 학문 세대인 학생들, 특별히 학부생들의 사진 공모전, 3D 프린팅 경진대회, 그리고 학생 작품전 등 심사를 통해서 우수한 작품들이 전시되고 있습니다. 두루두루 한번 방문해 주셔서 격려해 주시기를 부탁드리겠습니다. 우리 학회 12개의 위원회가 참여하는 위원회 행사를 비롯해서 연구단, 공공기관에서는 건축 안전, 건축 교육, 건축 기준, 지역 균형 발전, 특히 BIM과 관련된 최근의 어떤 현황들을 고려한 모듈러, 탄소 중립, 제로 에너지, 도립 미술관 건립 등을 주제로 최근 이슈와 연구 성과를 중심으로 세미나 및 발표회 등이 개최될 예정입니다. 그리고 조금 있다가 이 개회사가 끝나면 바로 이어질 키노트 스피커 특별 강연에 일본 내진공학의 전문가인 도쿄대 생산기술연구소의 나카노 요시아키 교수님께서 아마 일본의 건축물 내진대책 현황 및 최신 기술을 주제로 미래 세대를 위한 유익한 강연을 해 주실 것으로 생각이 됩니다. 나카노 선생님 감사합니다. 나카노 선생님 도모 아리가또 고자이마스. 이 외에도 강원지의 특별 세미나, 신진인재 교류회, 디지털 건축 대전, 건축 기술 대전, 교류회장 및 시상식 등 학회 준비위원회, 학술위원회에서 다양한 프로그램을 준비해 왔습니다. 그리고 매우 기쁜 마음으로 준비한 행사들을 진행할 예정이오니 아름다운 숲길, 그리고 절길거리가 풍족한 이곳 하이원에서 조금 바쁘신 일정을 내려두시고 휴식과 여유를 만끽하시기를 바랍니다. 이번 추계학술대회를 통해 우리 학회가 건축계 전반의 협력과 화합의 구심점으로서 건축 문화와 건축 산업의 발전에 기여하기를 기대하고, 특히 학술축제의 장인 학술 발표대회가 되도록 최선의 노력을 다하겠습니다. 이번 추계학술 발표대회 뭐라 해도 학술위원들의 노고를 취하지 않을 수 없습니다. 아마 학술준비위원들의 위원들의 노고가 없었다면 멀리 이곳 하이원에서 이번 추계학술 발표대회가 이처럼 세밀하고 풍족하게 준비되기가 어려웠을 것입니다. 또한 우리 학회 사무국 직원 여러분들 여기 잘 안 보이시는데요. 항상 세밀하게 준비를 해 주시는 점 이 자리에서도 감사 말씀을 거듭드리겠습니다. 모든 회원 여러분들께서 여유와 공기를 마음껏 마시고요, 즐기면서 늘 건강과 행복이 함께하기를 기원드리며 간단히 개회사에 대하겠습니다. 고맙습니다.
대단히 감사드립니다. 회장님의 일본어 발음이 아주 훌륭하신 것 같습니다. 예, 대단히 감사드립니다. 다음은 바쁘신 국정 업무에도 이번 추계학술발표대회를 축하를 해 주시기 위해 가지고 영상을 보내주셨습니다. 회장님께서도 말씀을 하셨는데 김진태 강원 특별자치도 도지사님의 축사가 있겠습니다. 영상 부탁드리겠습니다.
안녕하십니까. 강원특별자치도지사 김진태입니다. 2023 대한건축학회 추계학술발표대회 개최를 진심으로 축하드립니다. 대한건축학회 최창식 회장님, 관계자 여러분, 뜻깊은 행사 준비하시느라 고생 많으셨습니다. 이번 학술대회는 건축의 다양하고 새로운 정보 교류를 통해 건축산업과 문화의 발전 방향을 논의하는 대단히 중요한 자리라고 들었습니다. 오늘 행사가 건축계가 보다 잘 협력해 변화하는 건축 환경에 능동적으로 대응할 수 있는 뜻깊은 시간이 되길 바랍니다. 강원특별자치도의 건축산업 발전, 저도 함께 노력하겠습니다. 감사합니다.
큰 박수 부탁드리겠습니다. 도지사님 대단히 감사드립니다. 다음은 이번 추계학술발표대회를 축하해주기 위해 가지고 또 다른 영상을 보내주셨습니다. 김원영 강원대학교 총장님의 축사가 있겠습니다. 영상 부탁드립니다.
안녕하십니까. 강원대학교 총장 김원영입니다. 먼저 2023년 대한건축학회 추계학술발표대회 개최를 진심으로 축하드립니다. 이번 대회를 위해 수고하신 대한건축학회 최창식 회장님과 모든 회원님들께 깊은 감사의 인사를 전합니다. 대한건축학회는 1945년 창립 이래 지난 78년 동안 우리나라 건축 분야 발전에 핵심적인 역할을 담당해 왔습니다. 전문인재 양성, 학술 연구, 기술 개발과 글로벌 네트워크 구축을 통해 건축의 미래 비전을 제시하며 건축 산업의 성장과 함께 우리 국민의 삶의 질 향상에 기여하였습니다. 이번 학술 대회에서도 더욱 혁신적인 아이디어와 연구 성과들이 선보일 것으로 기대하며 이를 통해 미래 건축이 나아갈 발전 방향을 더욱 명확히 제시하는 뜻깊은 시간이 되기를 바랍니다. 강원대학교에서도 건축 분야의 연구 및 교육을 통해 대한건축학회가 열어나갈 미래와 새로운 도전에 함께 동행하겠습니다. 대한건축학회 추계학술발표대회 개최를 다시 한번 축하드리며 여러분 모두의 건강과 행복을 기원합니다. 감사합니다.
큰 박수 부탁드리겠습니다. 도지사님, 총장님의 축하 영상 대단히 감사드립니다. 다음은 김광우 전 회장님의 환영사가 있겠습니다. 큰 박수 부탁드리겠습니다.
여러분 안녕하십니까? 대한건축학회 전 회장 김광우입니다. 오늘 여러 기빈들과 수많은 회원 여러분들을 모시고 우리 학회의 2023년 추계학술발표대회를 성공적으로 개최하게 됨을 기원합니다. 먼저 이번 학술대회를 준비하신 최창식 회장님과 건축 발전에 대한 열의로 이 자리에 참석해 주신 내외분 여러분께 깊은 감사의 말씀을 드립니다. 1945년에 설립되어 올해로 78주년을 맞은 우리 학회는 이제 회원수 3만 명을 바라보는 역사적인 학회로 성장하였습니다. 우리 학회는 명실상부한 건축 분야 최고의 학회로서 우리나라의 건축 학문과 문화의 발전을 이끌어 왔습니다. 그리고 학술 발표대회는 언제나 그 선봉에 있었습니다. 이는 회원 여러분들의 헌신적이고 열정적인 활동의 결과라고 생각합니다. 앞으로 우리 학회가 저마다의 다양한 전문 분야에서 우리나라의 지속적인 발전을 이끌 것으로 확신합니다. 최근 국민의 안전과 행복한 건축 도시 공간 환경 조성에 대한 요구가 더욱 증대되고 있습니다. 또한 사회적인 패러다임도 변화하고 있습니다. 이러한 변화 속에서 우리 대한건축학회의 역할은 앞으로 더욱 더 중요해질 것입니다. 이 자리에 참석하신 여러분께 보다 막중한 책임과 사명감으로 학문 발전에 이바지해 주실 것을 당부드립니다. 앞으로도 학회는 회원 여러분들을 물심양면으로 지원하며 건축문화 발전에 앞장설 것입니다. 다시 한번 대한건축학회의 2023년 추계학술발표대회의 성공적인 개최를 축하드리며 이번 대회에서 논의되는 다양한 학문적 성과들이 우리와 국가의 삶을 보다 행복하게, 보다 안전하게 만들어주는 계기가 되기를 기원합니다. 감사합니다.
대단히 감사드립니다. 그럼 지금부터 학술 발표대회 개최를 기념하기 위한 특별 강연을 시작을 하도록 하겠습니다. 강연을 시작을 하기에 앞서 나카노 요시아키 도쿄대 교수님의 강연자 양력 소개가 있겠습니다. 양력은 사실 많이 있는데 간단하게 이렇게 추리기가 상당히 좀 어려웠습니다. 주요 양력을 중심으로 소개를 해드리도록 하겠습니다. 나카노 요시아키 교수님은 동경대 건축학과를 졸업을 하시고 같은 동경대 대학원에서 석사 학위를 포함해서 최종적으로 박사를 1989년도에 취득을 하셨습니다. 박사 학위를 취득을 하고 난 뒤에 28살이라는 아주 어린 나이에 동경대 생산기술연구소의 전임 강사를 시작으로 현재 정교수로 재직 중에 있습니다. 또한 현재 일본 방재과학기술연구소 내진공학연구센터의 센터장을 하시고 계시며 이전에는 동경대 생산기술연구소의 총괄소장을 역임을 하셨으며 일본 지진공학협회의 회장, 국제지진공학협회의 부회장, NPO 국제지진공학협회 감사관 등을 역임을 하셨습니다. 2021년에는 그런 공로가 인정이 되어 일본 방재부 장관, 한국으로 얘기하면 행안부겠죠. 행안부에서 방재 공로상을 수상을 하셨으며 지금 또 내진공학의 세계적인 전문가로 큰 활동을 하시고 계십니다. 가장 큰 학문적인 업적으로는 나카노 교수님의 스승님이시기도 하신 오카다 전 동경대 교수님과 일본 내진 진답법을 집대성한 공로입니다. 오늘 특별 강연의 주제는 영어로 이렇게 자료가 준비가 되어 있는데 Earthquake Engineering, Past, Present and Future라는 주제로 강연을 해 주시겠습니다. 그럼 나카노 요시아키 교수님을 단상으로 모시도록 하겠습니다. 큰 박수 다시 한번 부탁드리겠습니다. 오네가시마스. 제가 발음이 좀 더 좋은 것 같습니다. 예. 부탁드리겠습니다.
Good afternoon, everyone, and 안녕하십니까. My name is Yoshiaki Nakano from the Institute of Industrial Science, the University of Tokyo. And I'm also serving as a Director General of the eDefense, the largest shake table testing facility of National Research Institute for Earth Science and Disaster Resilience, shortly NIED. And first, thank you very much for kind introduction of me, Professor Lee. And also, I'd like to express my sincere thanks to Professor Che, the president of AIK, for having me here and giving me a good opportunity to talk a little bit about our experiences in Japan regarding earthquake engineering. Well, today I'm going to talk a little bit about these issues. First, a brief background history on the development of earthquake engineering after 1923 Kwanto earthquake in Japan. This year is 2023, so this is exactly the 101 century after this earthquake. And this earthquake was actually a very dawn for earthquake engineering in Japan. I will touch on it later, but anyway, well, I will talk a little bit about the background history and then lessons which we learned from past damaging earthquakes, seismometer network, seismic evaluation and rehabilitation, and also one of the important issues, continued function after a big event, as well as structural safety and resilient city. You may very often come across this word, but I would like to talk a little bit about this issue. And then lastly, future directions towards safer and more resilient city. For example, digital twin technology or more close collaboration with simulations and experiments. Well, this is showing a snapshot from the past damaging earthquakes in Japan. The left top is a Nobi earthquake in 1891, which occurred in the central part of Japan more than 100 years ago. And this earthquake was a very huge earthquake, and as you can see here, flattened almost all the timber houses at that time. So this was a very serious damage to the central part of Japan at that time. And also we have this one. This is a Kwanto earthquake which occurred in 1923, exactly 100 years ago. And even after that, we had a very serious damaging earthquakes, and even in a modern time, we have serious earthquake damage, like Kobe earthquake in 1995, and also even in recent years, we had a very huge tsunami damage because of the 2011 Tohoku earthquake or East Great Japan earthquake. And even recently in 2016, we had a Kumamoto earthquake, and this was also a very damaging earthquake, which centered in the southern part of Japan. And now I have picked up three major devastating earthquakes in Japan, and together with a major cause of these earthquakes. The top one is, again, Kwanto earthquake, which occurred in 1923. And the middle one is a Kobe earthquake in 1995. And the last one is a Tohoku earthquake in 2011. And the top one, Kwanto earthquake, the major cause of this, the fatality caused by this earthquake was a fire. But a fire was not just a simple fire, but how do you say? Here you can see something like a tornado, fire tornado was happened, and this tornado fire caused a huge number of deaths, and all the city was burned to ash. And in 1995, a Kobe earthquake, as you can see here, the major cause of the death or fatality was made by the building collapse. Here you can see the many building collapse situation here, right? And in the last pictures, you can see our devastating tsunami damage. And of course, this earthquake caused fatalities basically from the tsunami, and most people were drowned. And as you can see here, each disaster has a different face depending on the earthquake. Where the earthquake happens, when the earthquake happens, and how the earthquake happens. So every earthquake has a different faces in terms of that disaster. Now I can show you some background history and together with the damaging earthquakes and activities which were taken after the earthquakes. First I'd like to show the Kanto earthquake in 1923. And at that time, Japan was just under the rapid development or rapid growth of the urbanization of the city, like Tokyo or Yokohama area. They were very under the rapid growth or under the very rapid urbanization. But unfortunately, the city had a very serious damage. As I have told you, building collapse as well as a fire, a very big fire, caused many deaths in the city. And we understand that we need to introduce the earthquake engineering in the building construction. And after the earthquake, 1 year after the earthquake in 1924, a urban building law was updated, incorporating the seismic design regulation. As its name implies, urban building law, as its name implies, this law was applied only to 6 major cities, like Tokyo, Yokohama, Nagoya, Kyoto, Osaka, and Kobe. And after that, after the Fukui earthquake in 1948, building standard law was enacted in 1950. This time, this law was applied to building throughout Japan, unlike the urban building law that was enacted before in 1924. Oh, I'm sorry, I forget to press the button. Yeah, this is one picture from the Kanto earthquake. And then in 1968, we had a very epoch-making earthquake, which is named Tokachi-oki earthquake. Maybe this is something like a Pohang earthquake in Korea, because this was a very epoch-making earthquake in Japan. At that time, we had a very serious damage to modern building at that time. They were designed to, according to the most up-to-date seismic code. But new building, this damaged building was a new building, very new building, school building. But this building had a very serious damage, like a shear collapse in the first story. And this was a very shocking, and we understand that we have to consider more stringent rules or design concept for safer building. And one of the findings from this earthquake damage was that even if the buildings are designed according to the code at that time, the code was basically regulates the allowable stress design or working stress design. So eventually, we can complete the structural design even if we do not know the ultimate strength of the structure. So if a big earthquake happens, some buildings may survive, but some other buildings may not survive. So we have to understand the ultimate strength of the buildings. So, and another thing that we have learned from this earthquake is that if we have this kind of earthquake, again, in some other area which had not experienced the earthquake damage, then probably very similar damage will happen in different places. So the question is how we can identify, how we can find such a vulnerable buildings, and how we can do something, or retrofit such a vulnerable buildings before an event. So after this earthquake, we started the research on the seismic evaluation and the seismic retrofitting of structures. And in 1977, seismic evaluation standard and the rehabilitation guidelines were published, and we started to use these guidelines for seismic evaluation and retrofitting. And in 1981, the seismic code was revised in a drastic way, considering these experiences in the past damaging earthquakes. And Kobe earthquake in 1995. As you can see here, we had a very devastating damage to modern urban center like Kobe City. And fatalities were mostly due to the building collapse, as I have already mentioned. And various types of damage was found. Some, elevated highway was toppled down, and roof was collapsed, and also some buildings lost the first story. Very typical, one of the most typical failure pattern which can be found in everywhere in the world. And also timber houses were completely flattened. This damage was found everywhere in the epicentral area. Then what did we learn from this Kobe earthquake? We have learned a lot of things from this earthquake, damaging earthquake, but I would like to pick up three major things, issues. The first one is, first we should learn more, we should know more about ground motion themselves, and also structural responses themselves. This earthquake caused a very serious earthquake ground motion, and eventually it collapsed. Many buildings were collapsed. But how was such a killer quake or killer pulse generated? And also we have to collect data through robust seismometer network and structural test. And also, how did the structure collapse? Well, we can see the damaged structure after the earthquake, but we cannot see how they go into such a damage. The process was not clear, so we wanted to know how the structure collapsed, or process of the collapse was need to know. So after this earthquake, E-Defense, which is a very huge shake table testing facility, was idea of constructing such a huge testing facility was raised after this earthquake. And the second one is existing vulnerable buildings should be identified, and their seismic performance need to be upgraded. Seismic evaluation and rehabilitation of especially older building was highlighted. And such a structural safety is, of course, a very important thing and a must issue. But we also have to focus on the function after events. Well, as I told you, the collapse prevention is a must issue, highest priority. But buildings should be designed as users or owners who expect or wishes. Sometimes a building designer, structural designers say that the structure successfully survived the building if the building doesn't collapse, even if the building has some damage. But the building owner or building user do not want to have any damage. So the wish of the building owner or building user and structural designer's intention may sometimes have a gap in each other. So we have to pay more attention to the wish by the building owners or building users. And eventually we understand that performance-based design concept needs to be implemented. Then I will show you some examples regarding these issues. The first example is a robust seismometer network after Kobe earthquake, the development of K-net. K stands for Kyoshin. Kyoshin means strong motion in Japanese here. And before the Kobe earthquake, of course, we had some distribution of seismometer network here, but the network distribution was not so dense and not so uniform. And after the Kobe earthquake, we developed a densely distributed seismometers network. Each seismometer station was placed in an area of the 25 by 25 kilometer area, like this, so uniformly and more densely distributed after the Kobe earthquake. And more than 1,000 stations were installed throughout Japan. And this network started in operation in 1996. And these networks are fully utilized for earthquake early warning system, together with the Japan Meteorological Agency, JMA network, and so on. And this can warn us before you feel the shakings. Also, this network can provide a very variable information how the earthquake happened. This is showing the acceleration records of the 2011 Tohoku earthquake of 41 stations, which are located in one straight line here. And this record can help us understand earthquake sequence here. As you can see here, the first major fault rupture started here. The first major fault rupture started at Miyagi offshore here. And after that, second rupture, this blue line, second rupture started in, again, Miyagi offshore. And a difference in arrival time, here you can see the difference in arrival time of earthquake number 2 is less than that of earthquake number 1. I mean, blue line is a little bit flatter than purple line of the earthquake number 1. This means the epicenter's distance from the coast of earthquake number 2 is further than earthquake number 1. And also, the third rupture started in the area closer to the coast at Fukushima offshore area. And the difference of the arrival time is less flatter in this earthquake number 3. That means the epicenter is much closer to the coastal area than other two earthquakes. So we can understand in this way from these recorded data. And then now, in recent years, we have a new network development, which is called MOLAS, monitoring of waves on land and seafloor by NIED. For earthquakes, as I have introduced already, HyNet or KNet or KICnet or some other network systems are installed after Kobe earthquake. And for volcanoes, VNet is developed. And in recent years, after the 2011 Great East Japan earthquake or Tohoku earthquake, SNet or DoNet was developed for seafloor observation, both for earthquakes and tsunami. And in recent years, a new network called EnuNet is under construction. And these two, EnuNet and DoNet, are developed for a Nankai Trough earthquake, which is expected to occur in the very near future in Japan. And currently, more than 2,100 stations are operating, and they are serving as a source of, again, the early warning system and as well as researches. And also after the earthquake, Kobe earthquake, the construction of the large testing facilities, e-defense, the idea of this construction of the large-scale shaking table testing facility was raised. And this is showing the outline of the shake table test facility. table size is 20 meters by 15 meters, a very large shake table. And this is a real size, full size timber houses. And so you can imagine how large the shake table is. And this is a 3D, XYZ, and a 6 degree of freedom. That means rotation around the XYZ axis. So 3D and a 6 degree of freedom shaking can be generated. And this can simulate Kobe earthquake in 1995 and also Tohoku earthquake in 2011. And until now, more than 120 experiments were conducted in this e-defense. I will show you some example to what we have done in this e-defense. In the first phase of the e-defense testing, we did experiments to understand the collapse mechanism or collapse process, how the structures collapse. And we try to observe the collapse mechanism and also collapse process, as well as gathering data, scientific data. Then, Jason, すいません。最初のお願いします。The first one is a pier, highway pier, which was designed according to the 1970s technology. So this cannot resist the big shaking. The Kobe earthquake ground motion can easily destroy these old structures like this. And the failure pattern was exactly the same what we have observed after the Kobe earthquake. So we can reproduce the failure mechanism and the failure process. And after we applied a new technology, then of course the performance of this structure is much better than the previous one, and this doesn't have a serious damage like this. So we can confirm this kind of new approach is very effective to reduce or mitigate the damage to structures. 2つ目お願いします。And another one is a 3-story school building, reinforced concrete school building. As you can see here, the very typical shear failure was observed. And in the next video, you can see a close-up view of one column which fails in shear. And this is a school building, so in the next video, you can see the interior behavior of the classroom. And this is a reinforced concrete school building. And in the next slide, you can see the behavior of the steel structure, steel building. In the next video, you can see the very close-up view of the column which failed in large backing. So you can understand how the structure failed under the very big earthquake. And then the seismic evaluation. That second topic would be a seismic evaluation and rehabilitation program that started after Kobe earthquake. As I have repeatedly told you, fatalities are mostly due to the collapse of building designed according to the dated code before 1981. And the damage to those buildings designed under the new code revised in 1981 was minimized. They could survive successfully if the buildings were designed by the new code. So the question is how we can identify the vulnerable building which were designed according to the dated code. So seismic evaluation and seismic rehabilitation is needed. And this is showing the statistics, damage statistics after the Kobe earthquake regarding the damage ratio and also the age, year of the construction, design and construction. In the horizontal axis, you can see the year, and the vertical axis shows the number of buildings, and the darker color shows more serious damage to building structures. The black one is a heavy or even collapsed building. And as you can see here, the design code was revised in 1981. And after that, a new code, current code, that required seismic capacity is the same as we require in the current code. The same requirement is applied. And in the new, if the building was designed according to the new code, some building had some damage, moderate damage, but most of them survived in a very successful way. But if the building was designed according to the dated code here, the ratio of the more serious damage is getting higher. Of course, not everything is bad. Some building could survive, even if the building was designed according to the dated code. But we can say that if the building was designed according to the dated code, the possibility or probability of the higher damage is getting higher if the building was designed according to the dated code. So we understand that the target building for seismic evaluation and rehabilitation is those designed before 1981. And after that, we have developed and applied various types of retrofitting schemes to buildings. For reinforced concrete structures, most typical one is providing a reinforced concrete wall. This part was used to be an opening, but for seismic retrofitting, reinforced concrete was provided here, closing the windows. And in the next slide, here you can see bracing. In recent years, this type of steel-framed braces are most widely applied in Japan. And another scheme, weight reduction, is one of the promising technique because it can reduce the seismic force acting on the structure. This is a building that had a very serious damage in the mid-story, and after that, the upper part of the structure was removed, and eventually the structure became lighter than the original. So the seismic force is getting much lighter than before. So eventually the structure becomes stronger than original. For jacketing technique scheme, the white line is original column, reinforced concrete column, and the red one is jacketing material, which covers the existing original column. And also steel profile jacketing is also very often applied. This is a very original column, and by using a steel profile, then jacketed, and the gaps are filled with mortar. And these can provide or upgrade the confinement, and eventually they can provide a higher ductility, deformation capacity. And a carbon fiber jacketing or other band jacketing is also another technique which can also be applied to columns. And in recent years, isolation techniques are very often used for seismic retrofitting. Base isolation, not only the base isolation, but also the mid-story isolation techniques are very often applied. These techniques are very much applied, especially when that buildings needs to be operational or functional, even during the construction work. And also energy dissipating braces, something like a damper can be applied, especially in case of the buildings are a little bit higher than ordinary reinforced concrete structures. And these techniques are definitely effective to reduce the earthquake damage. As you can see here, these rehabilitation was definitely effective, for better performance during the 2011 Tohoku earthquake. The upper part building was not retrofitted before the earthquake and came to the complete, roughly, say, pancake-type collapse. But the buildings which were rehabilitated before the earthquake could successfully survive the earthquake. And I can show you one example for the timber houses. This was also made under the e-defense testing facility. And these two timber houses originally have the same design, but the right one was not retrofitted, and the left one was retrofitted. And the naturally retrofitted structures survived, but the non-retrofitted structures could not survive. So you can easily identify how the retrofitting is effective to the earthquake. And thanks to these activities, and also national program started in 1996, thanks to these activities, result in almost all buildings of upgraded school buildings. Here you can see the number of school buildings. The yellow one is non-rehabilitated school buildings. And the blue line is showing the ratio of the rehabilitated school buildings. As you can see here, the number of non-rehabilitated buildings are decreasing, and the ratio, almost all the school buildings meet the current code requirement, almost 100% in 2023. So these efforts resulted in almost 100% of the upgraded school buildings. But yet, in 85% of large capacity or user building. So private sector buildings are currently of most concern for further development of seismic rehabilitation in Japan. And another question is regarding the functionality. Well, the new code in 1981 worked well in Kobe. Well, obviously, it worked well for collapse prevention, but damage was found widely, ranging from no damage to near collapse. For example, this building had a damage here. This is a door opening here. And some buildings sustained serious damage to non-structural components, which are not designed to resist the earthquake loads. But even if it was not designed to resist the earthquake ground load, earthquake ground motion, once they are damaged like this, then this may cause a distortion of the door frame, and sometimes we cannot get in or get out of the room. So we cannot use the building until the repair is made. So this was a very big issue after this earthquake. So this is also another example, damage which were found throughout the building. This building was designed under the new code, in 1981 new code, and this didn't collapse with beam hinging. Here you can see a beam hinging, and we structural designer believe that this kind of beam hinging is a very good design, structural design. But actually, if we have this kind of beam hinging throughout the building along the height of the structure, then the damage is widely spreaded, widely distributed. Eventually, we have to repair many places. So the repair cost was too high, and the owner decided to demolish and reconstruct this building. So from the structural design point of view, this might be a successful example. But from the building user point of view, this is not necessarily the successful one. So as I have pointed out, some buildings were demolished and reconstructed because of the high repair cost, although they structurally performed well and as intended in the structural design. So the question is, just a collapse prevention is a task of the code. The answer is no. Structural safety is, of course, the first priority, the very most important things. But just not just the structural safety, but continued functionality is a very important issue. We recognize this issue, and a performance-based design needs to be developed and implemented. First, again, I'm going to show you some performance verification using the e-defense testing facility. じゃあお願いします。This is a 10-story reinforced concrete building, and this building was designed according to the conventional scheme, conventional design code. But as you can see here, there is no serious damage to column, but the beam ends or beam column joints have damage. And at this point, this part of the structure is a very difficult point to repair. So if we have this kind of damage throughout the structure, again, it may cost very much. And so improved design method was proposed and applied to this specimen, and we try to confirm the performance of the better performance of the structure using shake table testing. You may see a large deformation, but this deformation doesn't cause any serious damage to beam ends or beam column joints. So this kind of improved design method can work well even for this kind of mid-rise buildings. And then another issue is the functionality focusing on the facility operation aspect. This is the building, medical building, base isolated medical building. To maintain the operation of the building purpose, we have to reduce the damage, not only the structure, but also the damage to the facility inside the building. And we have compared two buildings, which one is base isolated, designed on a base isolated design, and the other one is a building designed according to the conventional seismic design. And obviously, you can see that left side building, which was base isolated, has a much less damage even to the facility. So you can keep the operation or function of the building. This kind of medical building needs to be operational immediately after the earthquake. So the base isolation system has a very big benefit for maintaining the function. And in 2000, performance-based design was enacted in Japan. And in 2011, Great East Japan earthquake happened. And this earthquake caused a very huge area damage, especially by tsunami. And the response and the recovery after the event was especially highlighted. Especially the word resilience was very much highlighted. And currently, these damaged areas are under reconstruction. And in some town, originally, this town had a 10-meter high seawall, but after the tsunami, they reconstructed a higher seawall, which has a 15-meter high. And also, in some other town, Otsuchi town, here we can see a high seawall here. And the inland area was elevated, but no buildings are standing yet. So this is a current situation of the reconstruction, not fully in good operation. But anyway, they are now under the reconstruction stage. And now the word resilience is a very key word in our society. the mitigation and the preparedness, it was a very key parameter in the conventional scheme. But in the conventional damage reduction model, damage can be defined by as a function of the hazard, exposure, and vulnerability. This is a very conventional idea for defining damage. But after these recent earthquakes, especially after the 2005 United Nations Disaster Risk Reduction Hyogo Framework, the word resilience was very much highlighted. The resilience is defined as a capacity or ability to prevent and recover quickly from the impacts. Here you can see a very schematic illustration of the resilience. The vertical axis is showing the functionality or performance, and the horizontal axis is showing time. Before an earthquake, the performance or functionality is here, 100%, and once you have the earthquake, if you have the damage, then functionality or the performance goes down here. And after that, recovery starts, and gradually the performance goes back to the original point. This is a very schematic illustration showing the idea or concept of the resilience. And in the resilience enhancement model, resilience can be defined not only the damage, but also the human activities like recovery activities and time, like this. And in recent years, especially after the 2015 UN DRR Sendai framework, we sometimes use the word build back better, together with resilience. I will touch on it later, but here you can see how this resilience can be achieved, higher resilience can be achieved. Yes, the objective is to minimize this red triangle area. If we could reduce the red triangle area, then we can say that we could have a better resilience. Then to achieve this, I may say two schemes, two options. One is the enhanced resistance, and this can reduce the damage like this. And then another option is to enhance the recovery capacity or recovery speed. This can reduce recovery time. And by combining these two schemes, we can minimize the red red triangle area for higher resilience. And in recent years, not just putting back to the original performance, but also we put it back to a better performance. This concept is often called build back better concept. We sometimes say not only to put it back to the original level, but we should consider how we can put it back better or build back better. This is a new concept that when we consider the recovery after the damage or disaster. And to achieve for this goal, to evaluate, to predict, and discuss the resilience of an entire city, we have to consider the multiple structures, not only a single structure, but a multiple structure. And once you have this kind of complex city, and if you have an earthquake here, the most serious damage would be happening in the epicenter area here. But if you go to the apart from the epicenter area, then you would have less damage, and eventually you would have a quicker recovery, like this. And eventually the area other than the epicenter could support the most seriously damaged area in the epicenter. So their interaction and social issues should also be considered for discussing the resilience of the entire city. And also long recovery time and eventually multiple events, especially after a large earthquake, should also be taken into account. So not a single structure, not a single event anymore, and we have to consider the very complicated simulations and the decision making are needed. These are very much needed. And to achieve this goal, simulation in cyberspace to virtually reproduce or model cities and to predict future events and disaster is undoubtedly very, very important, very essential. And the digital transformation with digital twin technology may be a very powerful tool for this purpose. Suppose now we have a target city here. This is a real-world physical space target city. And you can reproduce or model this city in a cyberspace. This is a digital copy of the target city, which may represent past and present. And by using this model, you can make a simulation. You can predict the future behavior of the city. And using this prediction, then you can update the model in the cyberspace. The most important thing is how you can quickly or how you can have a high cycle operation of this modeling and simulation, updating and simulation and so on. And a higher cycle simulation may require a simplified but a reliable model, even with high performance computing system. If you have a huge number of buildings in a city, and if you model the structure one by one using a very precise FEM model, it takes a long time to complete all the simulation. So you have to simplify the model. And high fidelity, not only the high fidelity model, but also mid fidelity models are also needed for simulation. But the question is, how can we convince that they are rationally correct? And of course, as I have told you, the simulation would be getting more and more important, and this is undoubtedly true. But nevertheless, I think experimental studies are very important because they are fundamental but essential for rational modeling and their updating to make reliable prediction. Then what is the best way to provide most reliable results? The answer is, I believe, is validation and verification. Validation means ensuring that your research methods and assumptions are appropriate and realistic for problems that you are going to solve. And verification means ensuring that your research outputs and calculations are accurate and reliable, correct? And validation and verification, shortly V&V, is key to ensure predicted results and to provide reliable results. So, but V&V eventually needs evidence-based data, so experiments is needed after all. So, for this, to achieve this objective, closer and more frequent and mutual two-way, rather than a one-way, communication should be formed between experimental researchers and simulation researchers. Not just relaying recorded data to simulation community, but the simulation community should identify parameters which is influential to the results. And also they should provide the experimental community with parameters which is needed to be clarified through experiments. The simulation community should provide information. This parameter is needed for better simulation, better, more precise simulation. So you should provide, experimental research community should give us such an information, which the simulation community should request such an information to the experimental community. So experimental community should improve or update test plans accordingly if necessary. And a mutual and even global communication ideas are most needed, especially for large-scale experiments to achieve the best cost performance. Because large-scale, especially the full-scale testing, is a very costly experiment. So we have to convince, for example, funding agency. This is a really informative. This test will really informative results. And also for such a case, not only a single institute or a single community, but also a larger community or a global community should contribute to have a common problem that we should tackle. This kind of collaboration or harmonization is very much needed in the future. Well, now I'd like to close my talk today. Well, over the past century, earthquake engineering in Japan has developed based on a damaging earthquake, say, bitter lessons, and a structural design, code development, seismic evaluation, and retrofit, performance-based design concepts, and so on are the keywords that we have learned from the past damaging earthquakes. And in recent years, achieving resilient cities has become a major challenge. And for this purpose, simulations with digital twin technology are key to predicting the resilience of cities to future events and making decisions. And simulation is getting more and more important. Definitely, this is true. But nevertheless, I believe experiments along with validation and verification is very essential for rational modeling and reliable results. And for this target, for this purpose, more emphasis should be placed on experiments, especially large-scale testing to provide evidence or data to validate and verify the model concerning data application to citywide simulation. And closer communication is most needed between experimental researchers and the simulation researchers, or I should say experimental community or simulation community for more advanced and reliable modeling. And sharing global ideas would also be a promising option for rational experimental design and maximum or best use of the data to address the common problems. And eDefense and AIJ are waiting for the global partners like AIK or Korean colleagues. Thank you very much for
대단히 감사드립니다. 도움 아리가토 고자이마시다. 시간이 조금 있어가지고요. 저를 아주 좋은 기회니까 한두 분 정도 혹시나마 질문이 있으실 것 같아요. 질문을 해주시면 되는데 영어를 하셔도 되고, 우리 또 최호 교수님이 또 계셔가지고 시주오카대에 또 오셔가지고 아주 오랫동안 일본에 사셨는데 한국어로 하시면 일본어로 하고 일본어로 받아가 또 한국어로도 이렇게 해드릴 테니까 질문 있으시면 한두 번 정도 시간 관계상 질문 부탁드릴게요. 있으시면. 그러면 질문은 나중에 또 이렇게 조금 정리를 또 하셔가지고 우리 이제 학회 홈페이지에 들어가시면 이메일이랑 아주 상세하게 정보가 있으니까요. 그쪽으로 또 이렇게 하시면 또 해소가 되실 수 있을 것 같습니다. 아주 훌륭한 강의, 결론 부분에 아마 모든 게 함축이 되어 있는 것 같습니다. 리질리언스, 그다음에 디지털 트윈 테크놀로지, 이런 것들은 이제 저희들이 추구를 해야만 되는 그런 미래의 새로운 패러다임이라고 생각을 또 하고 있습니다. 약 1시간, 2시간 구라이 너무 아리가토 고자이마시다. 큰 박수 좀 부탁드릴게요. 다시 한번.
감사합니다. Thank you.
소노마 샤신 아룬데. 예. 감사를 드리고요. 그러면 마지막으로 기념 촬영을 좀 하려고 그럽니다. 다들 단상에 올라오셔가지고 기념 촬영을 하고 난 뒤에 개회식 및 특별 강연의 모든 일정을 마치려고 합니다. 단상 위로 부탁드리겠습니다. 여러분들 단상 위로 올라오시죠. 기념 촬영을 하시고 마무리를 하시면 될 것 같습니다. 예.